And I'm very happy to introduce Juliana Setti from University of Maringá, Universidade Estadual de Maringá. She is a PhD student under supervision of the Professor Alexandre Santana. And today she will talk about control sets for affine control system. Juliana, go ahead.
Okay, thanks for presentation. I am beginner English student. I hope you understand me, but if necessary, Professor Alexandre will help us in the communication. I have joint work with Professors Fritz Colonius and Alexandre Santana, and we study about the control sets for bilinear and the affine control system. In particular, we study control sets with non-void interior and that contains an equilibrium point of the system. We study control sets for affine control system defined in Rn and the form 1. Here, A, B1 at Bm are real matrices, C1 at Cm in the vectors in Rn. The controls has value in the set omega. Omega is a subset of Rn. And the set of admissible controls is the set of real pictorialized constant function defined on R with values in omega. I remember some definitions, but these objectives were presented by professors Adriano and Josney. I just remember the unique solution for the system 1 starting in X is denoted by varphi xu, and the positive orbit of X is given by this equality, and the negative orbit of X is given by this equality. We denote by A of U this matrix, and a solution for this equation is an equilibrium point of the system 1 associated with the control value U. Note that if the determinant of A of U equal to 0, this equation has infinite solution or not has solution. Here, we consider that if the determinant of A of U equal to 0, then this equation not has solution. The set of real equilibrium point of the system 1 is denoted by E, and the 0 denotes the set of real equilibrium point associated with the control value U in interior of omega. We test is the control set. Here I remember the definition of control set. A subset D is a control set for the system 1 if it satisfies three properties. The property 1 is that for each x in D, there are a solution starting in X such that the solution belongs to in D for a positive time t. And the D is contained in closure of the positive orbit of X for all X in D. And the property 3 is that D is maximal with this property. Now I talk about results, and the first result is the classical result from Lee and Marcus. It says that if you consider a control system of the form 2, where f is differentiable, f00 equal to 0, and d0 is in interior of the control range omega, If the run condition 3 is satisfied, then the negative orbit of origin is open. Note that the run condition 3 is the well-known common run condition for linearized system at origin. So, if the linearized system at origin is controllable, then the negative orbit of origin is positive. In this lemma, we have that if you consider system 1 and the time reverse system 4, then the positive orbit of x determined by the system 1 is equal to negative orbit of x determined by system 4. So, we use these two results for obtain this proposition. In this proposition, we have that if you consider XU equilibrium point associated with U in interior of omega, and the linearized system at the XU is controllable, that is, the run condition 5 is satisfied, then the positive orbit and negative orbit of XU are open. Because if XU is an equilibrium point for the system 1, so XU is an equilibrium point for the system 4. So use this lemma for obtaining that the positive orbit is open, and the first results for obtaining that the negative orbit of XU is open. So a consequence of this proposition is that if you consider equilibrium point XU associated with U in interior of omega, then this intersection is a control set for the system 1, and the XU is in interior of this intersection. Here, we have that for each XU in associated with U in interior of omega, and that satisfies the run condition 5, there are a control set. But one this can be same of the other. So next result is about this. Here consider C a connect subset of the zero, and suppose that every equilibrium XU in C, U satisfies the run condition 5. In this case, there are a control set D containing C in the interior, and D is given by this intersection for every XU in C. Note that if XU, the run condition 5 is satisfied by 8XU for 8XU for U in interior of omega, if the run condition 5 is satisfied for 8XU in E0, so every connect component of E0 is contained in a control set for the system 1. In this lemma, we have situation where the control set is open or closed. Consider XU, equilibrium point associated with the control value U in interior of omega, and suppose that U satisfies the run condition 5. If every eigenvalue of A of U has negative real part, then negative orbit of XU is equal to Rn, And if every eigenvalue of A of U has positive real part, then positive orbit XU equal to Rn. In this case 1, a control set containing XU is given by closure of the positive orbit of XU, and in this case 2, the control set containing XU is the negative orbit of XU. In this case 1, the control set is closed, and in case 2, the control set is open. A consequence of this lemma is about the controllability property of the system 1. Suppose that there are control values u and v in interior of omega, and the equilibria xu and xv in the some connect component of A is 0, and suppose that every eigenvalue of A of U has negative real part, and every eigenvalue of A of V has positive real part. In this case, the system 1 is controllable. This results is proved by Muller in a special case, in this case here. Okay, an example, consider this system defined in R2 with scalar control, and suppose that for each U in interior of omega, U satisfies the run condition 5, and the A11 plus UB11 less than 0, and the A22 by UB22 greater than 0 for all U in omega. In this case, the system has a unique control set, and this control set is given by this Cartesian product. Here, XU, IU denote equilibrium point associated with U, and the XM, big M is the maximum of XU, X little m is the minimum of XU, Y big M is the maximum of YU, and the Y little m is the minimum of YU. Note that in this case, A11 plus UB11 less than 0, and the A22 and the A22 plus UB22 are eigenvalue of A of U in this case. In this corollary, we have that if you consider a control range compact and the interior of the control range is connected, and for every U, the matrix A of U has that 8 eigenvalue of A of U has real part different from 0. And every U in interior of the omega satisfies the run condition 5. In this case, we have that there are a control set containing 0, and in the next result, we will see that the condition 3 can be weakened. Here, we consider that the condition 1 of the previous corollary is satisfied, that is, the control range is compact, and the interior of omega is connected, and at most, finally, many points in interior of omega does not satisfy the run condition 5. If for all u in interior of omega, all eigenvalues of A of u has negative real parts, or if for all u in interior of omega, all eigenvalues of A of u has positive real part, that a control system contain E0 in the interior. In this case 1, the control set is closed. And in this case 2, the control set is open. In this theorem, we have a situation in that we have an unbounded control set. Consider C a connect subset of 0 and define omega C, the set of real control value u in interior of omega, such that xu is in C. Sorry. Assume that there is u0 in closure of omega of C, such that A of u0, determinant of A of u0 equal to 0, and C, u0 plus D is not in the range of A of u0. And every u in omega of C, different from u0, satisfies this run condition and the run condition 5. In this case, there are unbounded control set D containing C in the interior. Here, I present part of the results of our paper. This reference 2. In our most recent studies, we obtain results about the existence of bounded or unbounded control sets where the group of the system acts transitively on Rn. Thanks for attention.
Okay, let's thank Juliana. Any questions or comments? Okay, Adriano, go ahead.
Hi, Juliana. Nice work. I remember that we discussed something, but that's way far of what we discussed. It's really nice, your work with Alexandre and Fritz. And my question is, you said that basically if the matrix AU has 0 as eigenvalue for some U, yes, you have an unbounded control set. This is a sufficient condition, yes. Do you have some condition that also assures when the control set is bounded, in the sense that if you don't have this kind of if you don't have 0 as eigenvalues for n u, I mean, do you have an if and only if your control set is bounded, you cannot? Sorry. So if your control set's bounded, you cannot have this kind of function. So if you don't have this kind of function, do we have also bounded control sets? I mean, are the conditions equivalent?
Só um pouquinho, professor, que eu vou pedir para o professor Alexandre me ajudar a entender, que eu não entendo tudo em inglês.
But Adriano, you can ask in Portuguese now.
Ok. É que eu estou tentando formular as coisas, tem muita coisa acontecendo ao meu redor aqui. A pergunta é basicamente aquela condição que você tinha para existência de um conjunto de controle ilimitado, certo? Então, se existe se o alto espaço associado ao alto valor zero, para algum U zero, existe, é diferente do trivial, então você tem um conjunto de controle ilimitado. Vale a volta? Se você tem um conjunto de controle ilimitado, necessariamente existe esse tipo de função?
Não sei, professor, não sei dizer. A princípio, eu não sei, eu vou responder em português e o professor Alexandre traduz depois para os demais, tá? A princípio, o que nós sabemos é que se os pontos de equilíbrio têm ramos ilimitados, então, como você satisfaz a condição do ranking em cada ponto de equilíbrio, então você deve ter um conjunto controlado ilimitado. Essa é a condição. Você ter, basicamente é essa, você ter que o ramo dos equilíbrios são ilimitados, e em cada ponto você tem a condição satisfeita, então você deve ter um conjunto controlável que contém ele. Os resultados que a gente tem obtido mais recentemente tratam sobre isso, estabelecem condições, mas não nesse sentido que você perguntou. Não na volta. Ok?
Yes, I don't know, because for linear systems, you have this behavior of the solutions, and then you can see that when the eigenvalues are not they do not explode, you can somehow get rid of the central part, and then you have bounded control sets. So I would expect it something like that, because I don't know, when you change the control, you also change the matrix. So I don't know if you don't have this so nice behavior as linear control system. Probably the behavior is a little bit more erratic. So. Thanks.
Yeah, sure.
Okay, any more?
No Alexandre, Juliana, no caso 2-dimensional dá para ver mesmo esse teorema, né? Você pega os pontos de equilíbrio, você tem as soluções aproximando, assim, né? Em tempo positivo ou em tempo negativo, dependendo.
Isso, só que a gente não... Agora que a gente conseguiu... agora que eu consigo, de fato, provar que, no caso de dimensão 2, por exemplo, ali naquele exemplo, matrizes diagonais, se o conjunto de equilíbrio é conexo e compacto, então você tem um único conjunto controlável. Só que consigo provar a unicidade, porém, no caso que todos são positivos ou todos negativos, eu enxergo, mas não consigo descrever algebricamente quem são esses conjuntos controláveis. Diferente quando um é oposto do outro, que a gente tem o retângulo. Esse exemplo que eu trouxe é um caso do seu, né? Aliás, assim, é o contrário, né? O seu é um caso do meu, se eu zerar ali.
Do you hear me?
Okay. Yes.
Yeah. Great. Okay, what I wanted to say is that concerning Adriano's question, I do not think that equilibria are sufficient. One should also look at periodic solutions, something like the Floquet spectrum. So the growth rates for periodic solutions. But that is some work in progress. And I think then one can formulate a hyperbolicity condition, which then will lead to a sufficient condition for a bounded control set. Okay, thanks.
Just one.
Thanks for waiting such a long time.
Fritz, just one question. In this case, the Floquet spectrum is related with the eigenvalues of the matrix U. Yes.
Of the fundamental solution.
Okay. Thanks.
The fundamental solution of the homogeneous equation.
Okay. Samartin, have you some comments?
No.
Okay. Let's thank you, Julian, again.
Obrigada.